In this video, I'm going to talk about what moment of inertia is and how you find it for solids in case you are absent or in case you need more reinforcement on examples, or if we didn't get to examples in class today just for the sake of argument. Okay, so moment of inertia for point masses we learned the other day is this. That's supposed to be an I, sum of mr squared. That's for point masses. On the other hand, most objects aren't actually point masses. In fact, probably nothing is, only sometimes you can approximate things as that. So more practically, what you're going to do for a lot of questions is go to page 287 in your textbook. I'll wait. You actually need to go to page 287, I think. I think you can do that while you're watching this video. Okay, if you can't, what page 287 contains is a list of the moments of inertia for different types of solids. So for example, we have a solid, why am I doing this? There's a solid cylinder right over there. Okay, so that didn't erase very well, did it? Okay, so over here there's a solid cylinder, or at least probably that's what it is. The moment of inertia for a solid cylinder, it says on the table on page 287, is 1/2 mr squared. That is not something that I'm going to expect you to memorize or be able to derive. It's just what it is. The moment of inertia through the center of mass for a solid cylinder happens to be 1/2 mr squared, and the way that that's arrived at is actually through calculus. So you don't need to know how to do it. Somebody figured it out for you. The moment of inertia for different types of solids, though, is going to be different depending upon exactly what kind of a shape you're talking about. Like if it's a solid sphere, it's not that at all. For a solid sphere, instead of this 1/2 right here, it would be a 2/5 for a solid sphere. If it's a hollow sphere, then it's 3/5. So there's not really any good way to predict what that is. You're just going to have to look it up in your table. Okay, now, if you are rotating the object through its center of mass, that's what this cm is for, then the moment of inertia is something you can just look up in a table. But if it's like this one over here that I'm showing you, whoa, I didn't expect that to move that way. Well, there it is. Sorry, if we're looking at example 1, where the object is not rotating through its center of mass, right? If I were rotating through the center of mass, right, that would be along a line like that or so. This one's rotating off-center, which means that calculating the moment of inertia for it means looking at the parallel axis theorem. If you look back at the second worksheet, or the worksheet for homework 2, that moment of inertia was the formula for parallel axis theorem was this: ICM plus MD squared. All right, moment of inertia through the center of mass would be this right here. So I will take this and I'll just throw it into this formula if I want to find the moment of inertia for this example 1. Okay, but the MD squared part, that is going to be, well, the M is the mass of the cylinder, but the D is the distance between the center of mass and the pivot point. So that right there, that's going to be D. All right, let's say that D happens to be half of the radius of this cylinder. When we're talking about what is the moment of inertia, remember that is the resistance the object has to rotation. What the parallel axis theorem is telling you is that if you rotate it through somewhere other than the center of mass, the moment of inertia is always going to be greater by this right here. So the larger D is, the greater the final moment of inertia. In this particular case, since I picked r over 2, we're going to have 1/2 mr squared, all right, plus m times D, we said it's going to be r over 2. There it is. D is r over 2. Oh, and we're squaring it. Okay, so the final moment of inertia is going to be 1/2 mr squared plus, all right, when we're squaring this, remember it's like 1/2 squared, so we'll get 1/2 mr squared plus 1/4 mr squared for a total moment of inertia of 3/4 mr squared. All right, so that would be then the moment of inertia for this cylinder, which is not rotating through its center of mass. If it were rotating through its center of mass, again, we could just like use this formula right here, but since it's off-center, we're going to have to resort to the parallel axis theorem. All right, well, that's not what I want to happen at all. Okay, I want all that text to go away, and I want to just be looking at this next example here. So, oh golly, what's happening? Okay, let me just erase a whole bunch of crap. Excuse me, one moment, please. No, that's the wrong button. There's an erase button somewhere. Maybe just let me pause. Okay, and resuming. This is a new question where we've got more or less a pendulum, like you might have in a pendulum clock. And the thing down at the bottom, it says, is a cylinder. There it is. It's a cylinder. All right. And it says its mass is going to be 4m, and it has a radius of r. If you're like, what is m? What do you mean 4m? That's 4 times the mass of the rod that's holding the pendulum. And it says the length of that rod is 3r. All right. Now, the reason you need all that information is if you want to get the moment of inertia of this whole system, it's composed of 2 solids. In your table of moments of inertia, there were a bunch of different solid types, and one of them was a rod rotated about its end. Another one was a rod rotated about its center of mass, and then you had cylinders and hollow cylinders and stuff. Well, we're saying this is a solid cylinder, and then there's also a rod there. So the total moment of inertia is going to be whatever the moment of inertia for each of those objects individually would be added together. So we'll find the moment of inertia for the rod, and then here's the moment of inertia for the cylinder. All right, and those two things taken together are going to be the total moment of inertia for the system. All right, the rod. On page 287, you look up the moment of inertia and you discover it is 1/3 ml squared. Okay, that's cool. Oh, and then it says that L is 3r, so in a minute we'll plug in for that. The moment of inertia for the cylinder, though, we can't actually just use 1/2 mr squared. Would love to, but here's the center of mass of the cylinder. The pivot point is way the heck up here, which means that we're going to have to use that parallel axis theorem thing that we wrote down again. Okay, so for the cylinder, it's going to be parallel axis theorem. All right, here's what that's going to look like. Moment of inertia through the center of mass. 1/2 mr squared. All right, plus md squared. No, okay, so there we go. Fine, there's our moment of inertia for it. All right, 1/3 ml squared. All right, it says the mass of the rod, continuing over here, is just m. And its length is 3r. Well, let's square that. Okay, over here. All right, the mass of the cylinder is 4m. So that means that this m right here, we're going to have to replace with 4m. There it is. And its radius is r, so r squared. And then the d over here, I already labeled what that is, but if we sort of map out what that's going to be, it's r plus, it says the length is 3r, so plus another 3r. So that means the d is going to be 4d. So plus 4m times, I'm sorry, 4r, I mean to say, plus 4r squared. All right, so there it all is. All right, now we just have some simplifying to do. But when we're all done with this, what we will have is the moment of inertia for that entire pendulum. All right, the 3r squared, that's going to become 9r squared. And then we're dividing it by the 3 here. Okay, so we're going to have total from this term 3mr squared. All right, from this term, we'll have half of 4, so that's 2mr squared. All right, and now this last term. This one comes out huge because we took a very large mass and we're rotating it really far from the pivot, so its moment of inertia is very large. Altogether, that's going to be, whoops, I put that square in the wrong spot and nobody told me. Why did no one tell me that? And it won't erase. This is very sad. Why will it not erase? Oh gosh. I guess I'll just have to scribble over it. Okay, and then that square should have been out there, right? Because it's d squared, and I'm squaring 4r. So that whole thing is getting squared. So 4 squared, 16, times 4, 64 mr squared. All right, that means that the total moment of inertia is 3 plus 2 is 5 plus 64 is going to be 69 mr squared. That's a whole lot of inertia. All right, so again, to recap, we're finding moments of inertia for different types of solids. If you have 2 objects, their moments of inertia simply add, but you do need to take into account how they are pivoting, and in order to do that, you use this parallel axis theorem thing. In both of those examples, you saw that at play. So I hope that helped. This video should assist you with getting through that worksheet. Thank you very much.